All right, let's get straight into it. This is a technical breakdown of the Unified Modeling Language, or UML, class diagram. We're going to be focusing specifically on the syntax you'll encounter at the analysis level, giving you a clear reference for both reading and creating these essential diagrams. So take a look at this. This is a complete UML class diagram. Now, I know it can look a little intimidating at first, but our goal here is pretty simple. We're going to systematically deconstruct every single piece of this. By the end of this, you'll be able to read this and diagrams just like it with no problem. Let's begin with the most fundamental component.
Okay, so first things first. We're going to start with the absolute core building block of any class diagram, the basic class notation. Everything else we're going to talk about builds right on top of this.
So, what is a class? The easiest way to think about it is like a blueprint. You see, an object-oriented design, instead of defining every single object from scratch, we just create a class to act as a template. And any object we stamp out from that template, that's what we call an instance of that class.
Okay, so the notation itself is pretty standard. It's just a rectangle, and it's split into 3 compartments. Right at the top, you've got the class name. That's easy enough. The middle section lists out the attributes. You can think of these as the data or the properties that define the object state. And then down at the bottom, we have the operations, which are basically the behaviors or the things the object can do.
All right, so let's zoom in a bit on those middle and bottom compartments. We're going to break down the specific syntax used for attributes and operations, because there's a lot of important detail packed in there.
Okay, this diagram lays out the full syntax for us. Let's walk through it. For an attribute, you can see the format is visibility, then the name, its type, and sometimes an optional initial value. For an operation, it's pretty similar. Visibility, the name, a list of any parameters it takes in parentheses, and finally, its return type. Now, it's really important to get this. Every single symbol and keyword you see here has a precise, technical meaning. Let's break those down.
First up, visibility. This is specified with one of these 4 symbols. A plus sign, that means it's public, accessible by any other class. A minus sign means it's private, accessible only within the class itself. The hash symbol, that's for protected access, so the class and its subclasses can get to it. And finally, the tilde, that signifies package visibility.
Now, you might have noticed some of these members are underlined. This is a really critical distinction. That underline means it has class scope, or what most programmers would call a static member. What that tells you is that the attribute or operation belongs to the class itself, not to any one specific instance of that class. This is super common for things like utility functions, or constants, or maybe a counter that needs to keep track of all the instances that have been created.
Right, so a system isn't just a bunch of classes sitting there in isolation, right? The whole point is how they interact. So now we're going to look at class associations. These are the lines that connect classes and really define their relationships.
So what is an association, really? At its core, it's a structural relationship between classes. It's the model's way of saying that objects of these classes can be connected or linked up. And these links, well, they're the pathways that objects use to communicate, to send messages, and call each other's operations.
Visually, it's pretty simple, just a solid line. But you can add more detail to it. For instance, you can give the association a name, usually a verb phrase like employs. And you can even add a little triangle to show which way to read it. Another way to do it is to specify role names at each end, like employer and employee. This makes it super clear what part each class is playing in that relationship.
Okay, but this brings up a really common problem you'll run into when you're modeling. What do you do when the relationship itself has its own data? Take an employment relationship, for example. It's going to have things like a salary, a start date. These attributes don't really belong to the company class, and they don't really belong to the person class either. They belong to the connection between them. So how on earth do we represent that? And here's the solution. It's called an association class. The notation is very specific. You take a standard class box and you connect it to the association line with a dashed line. This lets us hang attributes and operations right on the relationship itself. It's a really clean and precise way to model these more complex data structures.
Okay, we're not done with associations yet. We can add even more detail and constraints. Let's talk about 2 really critical ones, multiplicity and navigability. So let's start with a basic question. How many instances of one class can be linked to a single instance of another? This is the core question that multiplicity is designed to answer. It's all about constraining the number of objects in a relationship. Now, being able to read these notations correctly is absolutely crucial. 1 means exactly 1. 0 dot star means 0 or more. We usually just say many.
1.star means 1 or more, and you can even specify exact ranges like 2.4. This isn't just a little detail on a drawing. This is where you formally define the core business rules of the system right inside the model.
All right, the next big question we need to ask is about data access. If I have an object of one class, can I get to the object it's linked to? This whole concept is called navigability.
Navigatingility is shown with an open arrowhead right on the association line. So if you see an arrow pointing from class A to class B, that means an object of class A can access or traverse to the object of class B that it's linked with. If you think in code, this usually means class A has a reference or a pointer to class B. And if there's no arrow, well, that means traversal in that direction is either not allowed or it's just not specified by the model.
Okay, we're on to the final type of relationship we're going to cover. This one is all about hierarchies. And we model this using something called generalization, which you probably know better as the basis for inheritance.
Generalization is how we model that classic is-a relationship. It's really the foundation of inheritance in any object-oriented system. You have the more general class, which we call the superclass or the parent, and then you have the more specific class, the subclass or child, which inherits everything, all the attributes, operations, and even relationships from its parent.
The notation for this is totally unambiguous. It's a solid line with a big hollow triangle at one end. And here's the key. The triangle always points to the superclass, the more general one. So in this diagram, you can read it as a square is a shape, a circle is a shape, and so on.
Now, take a closer look at the shape class name and some of its operations. See how they're in italics? That's not a stylistic choice. It has a very specific meaning. It tells us that they are abstract. An abstract class is basically an incomplete blueprint. You can't create a direct instance of it. Its entire purpose is to define a common interface that its concrete subclasses, like our square and circle, have to provide or implement.
So, that brings us to the big question. How does all of this precise syntax come together to let us model really complex real-world systems? We've gone through all the core elements, right? Classes, attributes, operations, all the different kinds of associations and hierarchies. The real power of UML here is in how you combine these strict syntactic rules. By doing this, architects and developers can build an unambiguous static model, just like that first one we saw, that serves as a solid blueprint for building software that's robust and, just as importantly, well-designed.